Hi viewers, welcome to today's class on mechanics of materials. In this class, I will be discussing normal strain and Hooke's law. Normal strain, it is the change in length of a material per unit length due to normal stress. So when a normal stress is acting on a material, the change in length to the original length, the ratio of change in length to the original length is known as normal strain or simply strain. So normal stress means it is a result of tensile or compressive stress. So when tensile or compressive stress is acting, there will be a deformation in the form of elongation or reduction in length. So this elongation or reduction in length, that is change in length. This change in length divided by original length of the material will give the strain. So when a bar is subjected to, say for example, tensile force, it will increase its length. So the length is increasing, that change in length you can measure, and the original length or initial length will be known. So the ratio of this change in length, in this case it is increasing length divided by initial length, will give the strain. That is going to be tensile strain, normal tensile strain. So due to tensile force, it is a tensile strain. Now if a compressive stress is acting, there will be a reduction in length, and this reduction in length divided by initial length will give the compressive strain. Since the strain is a ratio of change in length to the original length, the strain has no unit. So a normal strain is the ratio of change in length to the original length of a material when subjected to normal stress. Usually when you mention strain, it means normal strain. We will not specifically mention it is as normal strain. So strain is ratio of change in length to the original length, and it has no unit. Now what is the physical significance of strain? Okay, to understand the strain, let us consider a bar of 1 meter length and subjected to a pull at the bottom. So that is fixed, the bar is fixed at the top and subjected to a pull. So the initial length of the bar is 1 meter, and due to this pull, the bar elongates by 2 mm. Now what is the strain in this particular bar as a result of this pull? That is tensile force is acting, because fixed end will exert an opposing force. So the bar is under tension on the bar, tensile force is acting. So as a result of this tensile force, there is a 2 mm elongation, and that 2 mm elongation is in 1 meter length of the bar. Now to calculate the strain, you know the change in length and you know the initial length, you can take the ratio. So strain in this first bar is E1. I will just denote the strain by small e. It is E1 is 2 mm divided by 1 meter. Now this you cannot take it as 2 by 1, because 2 is in, it is mm, and 1 is, the length of the bar is in meter. So you need to convert into same units before cancelling the units. So 1 meter is 1000 mm, or 2 mm divided by 1000 mm, or it is 2 into 10 raised to minus 3. This mm cancels, you get the strain in the first bar as 2 into 10 raised to minus 3. Now what is this 2 into 10 raised to minus 3 stands for? 2 mm means you can easily understand that it is the increasing length in the entire length of the bar. Now what is 2 into 10 raised to minus 3, or 0.002? It is 0.002. What is that 0.002 stands for? 2 mm is the increasing length in 1 meter length. What is the increasing length in 1 mm length of the bar? due to this force, how much elongation is taking place if you take 1 mm length of the bar, that is unit length of the bar, how much elongation is taking place in that 1 mm length, that is 0.002 mm. 1 mm length, it will elongate by 0.002 mm. Or if you are taking the unit as centimeter, 1 centimeter length, the bar will elongate by 0.002 centimeter. If you use centimeter for the length, then even the elongation will be in centimeter. So this quantity denotes the elongation produced in unit length of the bar. So I have shown another bar which is 1.5 meter long, and due to the axial pull it elongates by 2.8 mm. 2.8 mm. Now in that case, strain in that bar is 2.8 mm by the initial length is 1.5 meter, so you get the strain as 2.8 mm by 1.5 meter is 1500 mm. You need to multiply by 1000, so you get 1.867 into 10 raised to minus 3. So this quantity denotes the deformation in unit length. So that means 1.867 into 10 raised to minus 3 mm is the elongation in 1 mm length of the bar. So without calculating this strain, if you see these two bars, how do you judge that which bar is undergoing maximum deformation or maximum elongation? Apparently this is undergoing maximum deformation because it is undergoing 2.8 mm elongation compared to this. Say if the bars were of equal length, which would have undergone maximum deformation. Okay, this deformation is 1 meter length and this is in 1.5 meter length. This may be of different material and the forces may be different. We are only comparing the deformation produced. So total deformation is, this bar is undergoing maximum deformation, no doubt about it, because it's 2 mm, this is 2.8 mm. But what is the deformation produced in unit length, in 1 millimeter length or 1 centimeter length or 1 meter length? So suppose this bar was of 1 meter length, what would have been the deformation? That you can get it from this strain. 1.867 into 10 raised to minus 3 meter in 1 meter length. So this bar, if I take the length as meter, 1.867 into 10 raised to minus 3 meter in every meter length. So 1.867 into 10 raised to minus 3 meter means 1.867 mm in 1 meter length. In 1 meter length, it will undergo 1.867 mm, whereas this in 1 meter length is elongating by 2 mm. So this undergoes less deformation in unit length, or these quantities you compare. Now this strain in unit length, the second bar is having less value compared to the strain in the first bar. So this has less deformation. This bar is undergoing less deformation in unit length. Total deformation is more, but in unit length this bar is undergoing, second bar is undergoing less deformation. So to compare the deformation produced in between two different or different bars, different structures, you can use the quantity strain. That is the significance of strain. Now coming to Hooke's law, it states that the stress is directly proportional to strain within the proportional limit or elastic limit. So if the material is loaded within the elastic limit or proportional limit, the stress is always proportional to strain, directly proportional to strain. Okay, so what is the elastic limit? Elastic limit is, or proportional limit, it is more or less same point when material is loaded. So when you load a material, up to certain point, on removal of load, the material will regain its original shape. At this point of loading is elastic limit. Okay, so if material loading is exceeded beyond the elastic limit, the material will not regain its original shape. For example, if you take a rubber band and pull it, so a small amount of force you apply, and on removal of load, the rubber band will regain its initial shape. But if you apply more force, there will be a permanent deformation. So that means if you are going beyond the elastic limit, the material deforms and permanent deformation takes place. So the loading should be within the elastic limit or proportional limit. Proportional limit means where the proportionality between stress and strain exists. Proportionality, that means if you take a bar and apply tensile force, and if it elongates 1 mm when you apply 100 Newton load, 1 mm elongation when you apply 100 Newton load, and if you apply 200 Newton, if it elongates by 2 mm, and if you increase the load to 300 Newton, it elongates by 3 mm, then the proportionality exists. So every 100 Newton the elongation is increasing by 1 mm. But when it is 400 Newton, if the elongation is 6 mm, so that proportionality has gone. So the proportional limit is as long as the stress is directly proportional, or load is proportional to deformation in a material, then you can say it is within the proportional limit. So proportional limit and elastic limit are more or less same. It is interchangeably used in mechanics of materials, and Hooke's law is valid till that proportional limit or elastic limit. So this is, we are talking about normal stress and normal strain. So not specifically mentioned, the Hooke's law states that normal stress is directly proportional to normal strain as long as the loading is within the elastic limit, where the proportionally constant is known as Young's modulus or modulus of elasticity. Okay. So sigma is equal to EE, and capital E is Young's modulus or modulus of elasticity, and you can rearrange this equation and you can write capital E as sigma by E. Sigma by E, Young's modulus is equal to sigma by E. So you can define Young's modulus as ratio of or calculate Young's modulus as ratio of stress divided by strain, but you can apply this equation only within the elastic limit. So you can define Young's modulus as ratio of normal stress to normal strain. Ratio of normal stress to normal strain is Young's modulus, and since strain has no unit, Young's modulus has same unit of stress, because Young's modulus is sigma by E. E has no unit, so whatever unit stress is having, the same unit even Young's modulus will have. So the unit of Young's modulus is expressed in Newton per mm square or megapascal. Newton per mm square and megapascal are same. I have shown it in the previous class. Now you can measure the change in length of a bar of uniform cross section from Hooke's law. So let us consider a bar of uniform cross section subjected to an axial pull P. Now as long as the loading is within the elastic limit or proportional limit, you can apply Hooke's law and you can write sigma is equal to capital E into E, or sigma is equal to EE. Now you know sigma is equal to, that is a stress, normal stress is equal to load divided by cross sectional area or resisting area. So stress is P by A, you can write stress as P by A, and strain is the deformation produced in unit length, you can write it as delta L by L. So stress and strain you are getting, and once you get the stress and strain, you can find out the deformation by substituting. You substitute stress as P by A and strain as delta L by L. So substituting in that formula, you get P by A is equal to E into delta L by L, and rearranging this equation, you get delta L is equal to PL by AE. So you can find out delta L is change in length, and you can find out the change in length as PL by AE, where P is the axial load applied, L is the length of the bar, and A is the area of cross section, and E is the Young's modulus of elasticity of the material. So this helps us to predict the change in length due to axial load on a uniform cross section bar without actually conducting the experiment. Without physically conducting the experiment, you will be able to predict the deformation produced once you know the Young's modulus of elasticity, that is material property, and other parameters like load, length, physical measurement, that is length and cross section area. So otherwise, if you have to get the elongation produced, you have to physically conduct the experiment. You have to pull the bar and measure the elongation. But without doing that, you will be able to predict the elongation or predict the change in length. So it can be elongation or reduction in length. So if a compressive load is acting, it will reduce the length. So you will be able to predict the change in length without physically conducting the experiment. You cannot always conduct a test in structures when you design a structure to predetermine the deformation produced in the structure due to various loads. You cannot always construct the structure and measure the deformation. If you can calculate the deformation in advance, that will help us. So to do that, you should know the property of the material, that is Young's modulus. So how do you determine Young's modulus? So to determine the Young's modulus, you should test that material in advance. You should conduct a test, and as you know, Young's modulus is stress by strain. So normal stress by normal strain within the elastic limit. So you should apply load and measure the deformation produced, and calculate the stress and strain, then take the ratio of stress to strain. That will give the Young's modulus as long as the loading is within the elastic limit. So once you know the Young's modulus, you will be able to predict the deformation produced. That's for today's class. Thank you for watching.